Hey guys, welcome back to Pop 'em Up Chem. We're soldering on with Unit 9 and 19 redox processes, and in this lesson we're going to be looking at redox titrations. As always, share the video, comment, like, subscribe, and hit the bell icon. Let's get on with it. Okay, so in this video we're going to look at how these combined redox equations can be used to find an endpoint. We're going to describe redox titration calculations, and then we're going to carry out some of these calculations and also apply them to the Winkler method. As always, question up top for you to have a go at. Considering these reactions, determine the order of reactivity and identify the best oxidizing agent. Pause the video to give yourself a moment for that. Okay, let's break that question down then. So we're given these three reactions, and in the first reaction, we can see that CD loses electrons. So CD must be more reactive than nickel here. In the second reaction, we can see that nickel is more reactive than silver. So therefore, silver must be less reactive than nickel. And in the last reaction, we can see zinc is more reactive than cadmium. And then we can just write this out as a list comparing the reactivity. As for oxidizing agent, we know an oxidizing agent is something that gets reduced. So the thing that is most likely to get reduced here is the thing that is most likely to gain electrons. And the thing that is most likely to gain electrons was our Ag+. And for our reducing agent is, of course, the thing most likely to be oxidized. Being oxidized is the most likely to lose electrons, and the most likely to lose electrons was, of course, our zinc. Brilliant. So before we get started, let's have a look at a recap of redox equations. So I've got two equations here, and I'm going to use the list that we did. Balance, water, H+, electrons, and OH-. And I'm just going to do that for both equations. Remember, always go through, and we always assume we have an acidic solution unless otherwise stated. In this case, I need to multiply the second equation by 5 to get the same number of electrons, and then I can combine both equations into a balanced redox equation. In fact, we're going to look at this exact equation now. Make sure that you've got this kind of method really wrapped up by now, and if not, go back and check those videos. So we can use this kind of reaction to be able to determine the concentration of different ions in a sample. So here we can look at iron, but it could be another sample. And this reaction is auto-indicative. It auto-indicates, and that is, we don't have to add a separate indicator because the change in oxidation state is going to change the color of the manganese ions, and that is going to tell us when the endpoint has been reached. So we can use this in an assay to determine the concentration. So an example of doing this might be to crush up a tablet, dissolve that tablet in sulfuric acid, and then that solution is made up to a known volume, and then we can use a volumetric flask for that, and we can then titrate it. And then from that titration, using a standard solution, we're able to work out the exact concentration and mass in the sample. So we're actually going to use a rather familiar looking titration to do this. So in the burette, we have our solution of potassium permanganate, and this is going to be of a known volume, the known volume being the titer, and a known concentration. This has a purple color from the manganese with an oxidation state of +7. In the bottom, we're going to have the solution of, in this case, iron tablet crushed up and dissolved in the sulfuric acid, and this is colorless. So we don't know the concentration of this, but we do know the volume. So what we can start doing is we can start adding up a manganate dropwise, and while that's happening, every time the manganese ions fall into solution, we're going from the MnO4 to Mn2+. So we're changing the oxidation state. So it goes from purple to colorless as soon as it lands, because the Fe2+ in solution allow the reduction of the Mn ions. And so what that means is slowly but surely we keep adding permanganate, and that removes more and more Fe2+ from solution. And at a certain point, we're going to reach a point at which all of the Fe2+ ions have been used up. And at that point, the solution in the conical flask is going to turn purple. And that is the end point, because now we'll have a known concentration and a known volume, which is our titer of potassium permanganate. And then we can use this equation to go ahead and calculate the unknown concentration of iron. So you'll remember from our titration calculations that it's the ratio of permanganate ions to iron ions that is going to help us with our calculations. And we've got a 5:1 ratio here. And we're going to look at a method of how to complete this calculation and have a little bit of practice. Okay, so here's an example question. In this one, we've got an iron nail that we're trying to determine the percentage by mass of iron of. So the first thing I'm going to do is I'm going to read through this question, and I'm going to highlight the important information from the question. That's always key for us to be able to do the calculation correctly. So we can see the mass of the nail was dissolved in 100 centimeters cubed of acid, and then 10 centimeters cubed of that solution were titrated with potassium permanganate, which had a concentration of 0.02, and our average titer was 9.8. So what steps do we take to get this done? Well, we're going to be using C1V1 over N1 equals C2V2 over N2, our titration calculation. So I'm going to do my concentration multiplied by my volume of the permanganate is equal to the unknown concentration multiplied by the volume over the number of moles of the iron ions, which is the concentration of Fe2+, which I get 0.084. Once I've done that first step, I'm then going to want to find my number of moles of Fe2+. So I'm going to convert that number of moles. So I need to find that, which is going to be my concentration times my volume, which is going to give me 9.8 times 10 to the minus 4 moles of Fe2+. Next, I'm going to want my moles in the sample. Now, this is a common step that people forget. Look, we dissolved it originally in 100 centimeters cubed of acid, and we only titrated 10 centimeters cubed portions. So we need to account for the fact that our titration only accounts for a fraction of the initial volume we dissolved it in. So all we need to do here in this case is multiply our number of moles by our ratio, our dilution factor. So we just times it by 10 in this case. So we get 9.8 times 10 to the negative 3 moles. And now we just need to find the mass of iron in that sample, so we need to now convert that number of moles into a mass using the molecular mass of iron, which is 55.8. Then I get 5.47 grams. Could be the answer to the question. However, I bolded it. What is the percentage by mass of iron in the nail? So we just need to do a percentage by mass of iron. So 0.547 divided by 2.41 multiplied by 100 is going to be equal to 22.6%. So we have 5 overall steps to get that done. Find the concentration of the iron, find the number of moles of the iron in our titration, work that back to find your moles in your sample, which you then convert to a mass in step 4, and find the percentage mass in step 5. Okay, so time for you to have a go at one of these now. So it's a long question, so make sure you take your time to get all the information you require to complete the question, and just relax and go through the steps that we just covered. Pause the video here to give yourself a few minutes to complete that. Fantastic. going through these 5 steps then. Firstly, we're going to use our titration calculation and the values given to us in the question. We've converted the values in this calculation to decimeters before we've put them into the calculation, and that gives us a concentration of 0.12 moles per decimeter. Step 2 is, once we've got that concentration, we want to work out the exact number of moles that equates to. So we're just going to multiply that by the volume, which gives us 1.2 times 10 to the minus 3 moles. And remember, we need to convert that by the dilution factor to find the moles in the original sample, which is just times by 10 in this case. For step 4, we want to find the actual mass in that nail. So then we're going to multiply that by the molecular mass of iron, which gives us 0.569 grams. And again, it's asking us about the percentage by mass of iron in the nail. So we're just going to do 0.059 divided by the initial mass of the nail, all multiplied by 100, which gives us 40.4%. Awesome. So although it might be a little long-winded, these questions aren't actually too complicated. We're just repurposing our old equations. So we can use permanganate as we've been using in these examples, or we can use chromium ions. And this is because the change in oxidation state of these ions shows a color, and this allows a self-indication. In chromium, we go from orange to green, and permanganate, we go from purple to colorless. That's what allows these to auto-indicate and allows us to use them for these titration calculations. So now that we've done those calculations, we're going to turn our attention to the Winkler method. Now, the Winkler method is used to calculate dissolved oxygen in water samples using techniques not too dissimilar from the ones we've looked at. Now, high oxygen levels are an indication of water quality and water system health. So, the more dissolved oxygen, the more healthy a water system and the lower pollution is considered. But we can also use being able to find dissolved oxygen to find the biological oxygen demand, the BOD. And as pollution increases, this tends to increase because the more oxygen a sample of water requires over a period of time, the more that indicates that there's microorganisms inside the water that are requiring that oxygen for the breakdown of organic matter. And the more organic matter is in a water system, the more polluted the water system. So we have dissolved oxygen, which is the amount of oxygen, and we have the biological oxygen demand, which is the amount of oxygen that the water requires to fuel these processes. So let's go through the Winkler method process. Now, you do not have to remember this process off by heart, but you do need to know the relationship that the reactions show. So the first step that we need to do is we need to fix oxygen. Okay, oxygen is not going to react in a redox equation by itself. So we're going to add a manganese salt in a basic solution. So that's with hydroxide. And what this is going to do is this is going to fix the dissolved oxygen, the O2 aqueous, and react it with the manganese to form MnO2. So now we have a solid precipitate in the form of MnO2. We're going to add acidified iodide ions. And what these are going to do is these are going to react with the MnO2, and they're going to form I2, which is of course brown in aqueous solution. And it's this that we're going to look at into the final step and carry out our titration to be able to work out the concentration. So in the final step, we're going to titrate the iodine that's been formed with sodium thiosulfate. And what this allows us to do is to determine, using a standard solution of sodium thiosulfate, the exact concentration of I2. And that's the same I2 that was in the middle equation, which was formed from the MnO2 in the first equation. So we have a relationship of 2 to 1, 1 to 1, and 2 to 1 again. So this gives us, for the whole process, an overall ratio of 4 to 1. That means for every 1 mole of dissolved oxygen that was in the sample, there will be 4 moles of thiosulfate in the final titration. And it's that ratio that you really need to etch into your mind when thinking about doing these calculations. So what does a question actually look like? Well, personally, I think these questions are actually slightly easier than the redox titration calculations we had a look at. So this is what they look like. I've put the equations here so that you can see them. And how do we go about it? Well, the first thing we want to do is, of course, find our useful information. So that's my volume of water and my concentration and volume of sodium thiosulfate that it was titrated with. And it wants the answer in grams per decimeter. So first step, I'm going to find my number of moles of thiosulfate. So I do my concentration times my volume, which is 0.05, multiplied by 0.125, converting to decimeters, which gives us 6.25 times 10 to the minus 4. Then I'm just simply going to use that ratio, that 4 to 1 ratio, going back through the equations, 2 to 1, 1 to 1, 2 to 1. And that just means I divide that number by 4 that I got in my part 1, which gives me 1.5625 times 10 to the minus 4. And that's in moles. And I want to express it in grams per decimeter. So the first thing I'm going to do is I want to work out my number of moles of O2. So all I need to do there is multiply it by the MR, which gives me the number of moles. However, look up in your question, that is only for half a litre. So to find per decimeter, I'm going to divide that by 0.5, which is going to give me 1 times 10 to the minus 2, or 0.01 grams per decimeter. Fantastic. You know what time it is though? It's time for you to do one. Let's have a go. I'm not going to read it out to you, but it's set up in a very, very similar way. So read through it, get the information that you need from it, remember your ratio, and look at what the question's asking for. Pause the video here to give yourself a moment for that. Okay, let's go through it then. Okay, so highlighting the volume of the sample and the concentration of volume of thiosulfate, and we need it in grams per decimeter again. First of all, finding our number of moles of thiosulfate, we're just going to do volume times concentration, converted to decimeters of course, which is 2.5 times 10 to the minus 4 moles. And then I'm just going to use my ratio and divide that by 4 to give me 6.25 times 10 to the minus 5. And of course, we want grams per decimeter, so we're going to convert that number of moles into a mass by using the molecular mass of O2. And not forgetting to also count our volume of water and dividing it by the volume in decimeters, which gives us 8 times 10 to the minus 3 grams per decimeter. But you already knew that. Well done, guys. So again, by popular demand, here is an exam question on this. Pause it, give yourself some time to have a go. Okay, so all we're going to do here is we're going to take the number of moles of iodine formed in step 3 and determine the amount of oxygen. We're going to divide it by 4, remember, which gives us 3.75 times 10 to the minus 5. And to determine the solubility, all we're going to do is we're going to turn that into grams per decimeter. Remember, we're just going to multiply it by the molecular mass of oxygen and divide it by the volume given to us in the sample, which gives us 6.00 times 10 to the minus 3. Nice one. So really well done here, guys. I know these questions are kind of long-winded, and so they just take a little bit of time to crack. As always, you really need to be doing practice, focused practice on questions of this. So we've done about redox titrations and their auto-indicating nature and the Winkler method. Thanks again for joining me. Please share this video, share what you think about it in the comment section below. Let me know if you'd like to see anything else from the channel. And as always, practice makes slightly better.